Today we will learn the mesh filter, the performance of mesh filter in at the receiver. Actually we have to use a block diagram in which we, as shown in this slide, we would use the meshed filter, just two branches. I'll discuss this two branch receiver. We will have mesh filter in the upper branch. We would denote it by H0 of T, and a mesh filter in the lower branch, and we would denote it by H sub 1 of T. So we actually received a signal R of T at the receiver, and we would like to pass it through this two branch mesh filter receiver, and then the output of the mesh filter would be sampled at instant T. The output would be sampled at instant T in the upper branch as well as in the lower branch, and we would see that these two outputs which we take from these two branches, these two outputs would be given to the detector. So we would have a detector here. This is a detector block for the purpose of detection. So actually the meshed filter receiver, which is known as the optimum receiver in AWGN, it is known as the optimum receiver in AWGN channel would be discussed today. For actually what we have to derive, we are expecting to derive this response, this filter response, right? So we would derive the filter response H sub 0 of T and H sub 1 of T, and actually we would see that when we have the meshed filter, the output which we get over here, it is very similar to the signal correlator, or the output of the meshed filter at these points when it is sampled at instant t equal to t0, it is same as the signal correlator. So actually the meshed filter receiver, the performance of the meshed filter is same as the signal correlator, and this is the optimum receiver which we observe in additive wide Gaussian noise channel. The signals which would be transmitted are for today's lecture we take two signals. We assume that our signal SI of T is one of these two signals. It is either S0 of T or S1 of T, right? So we have two waveforms, S0 of T and S1 of T, in this duration 0 to capital T, right? So we and we can say that we are transmitting S0 of T for binary 1, and we are transmitting S1 of T for binary 0. So for binary 1 we have we transmit S0 of T, and for binary 0 we transmit another waveform, a baseband signal S1 of T. Now here we also assume that S0 of T and S1 of T are orthogonal, right? So we assume that S0 of T and S1 of T are orthogonal. So these two waveforms are orthogonal, and specifically, to be very specific, let's assume that S naught of t, let's assume that S naught of t is a pulse from 0 to capital T, right? This is my S naught of t, which is a pulse with amplitude A from 0 to capital T. And suppose S1 of t is another pulse, which is actually this from 0 to capital T, and this is my S1 of t. So suppose we are transmitting these two signals, and you can always verify the orthogonality of these two signals. Now for these signals, we would like to derive the response, the mesh filter response, right? For these two signals, we would like to derive the mesh filter response, which is H naught of t and H1 of t in the lower branch. Well, from the theory of the mesh filter, if you go through the detailed derivations of the mesh filter response, we conclude, you can conclude that the filter response, the filter response for a mesh filter should be in this form. It should be in this form. Which essentially this is from between 0 to capital T, right? Capital T or T bit interval, right? So you can use the capital T or TB bit interval. So if you are using T, it should be T here. If you are using TB, it should be TB here, right? So we have used T. So let me erase this B from here. Let me erase this B, right? And we would see the response. Okay. So this is from T between this interval 0 to T. So this is the mesh filter response. Essentially, our mesh filter should be the mesh filter response is given here by this equation, which means that the mesh filter, the filter response would match your signal, and it matches your signal only when it is the in the time inverted and shifted version, of your signal. When your response, filter response, is the time inverted C minus T and the shifted version plus T, shifted version of your signal. So now we have assumed that we have two signals, S naught of T and S1 of T. So we can derive the, we can find the response for our waveforms S naught of T. So if we have S naught of T, it means that the mesh filter response for S naught of T should be equal to S naught of T minus T. So this we have, if we have a filter with response given by this equation that is meshed, that would give us an output which is meshed to S naught of T. And also keep this in mind, that the output of the meshed filter, is always it gives you the maximum SNR. So the output of the mesh filter would give you the maximum SNR, which means the output is actually when we take the sample, if you go back to the your figure, if you take that sample, that instant, at that particular instant, we have the maximum SNR. We ensure that the SNR at this instant is maximum. So this is all from this maximum SNR is only obtained at the output when your response is given by this equation, which means that your filter response should be equal to the time inverted and shifted version of your signal. So this is essential. Essential for getting the maximum SNR output from the filter. So you are familiar, as a general discussion, just me recall your previous knowledge that you are familiar with the concept of if you have some filter and it has certain output, certain input, and it has certain output y of t, you can always write the output of the filter as a convolution of x of t and its impulse response. So it is the convolution. Your output y of t is the convolution of x of t and h of t, right? And when you do this convolution, you can always write it. You are familiar with the concept of the convolution, that you can write this signal as an integral, right? This convolution is actually an integral. And how to write that integral? First of all, you convert your x of t into x of tau. X of tau, you just replace t by tau, another variable. Similarly, your h of t, convert it into h of tau, right? So these two is just a conversion of your just you use another variable tau for this is the first step of the of writing the convolution integral. So you can now, once you do it, x of tau and h of tau, the next step is to write your integral. And how you write the integral? That is multiply x of tau with the shifted version h of now when you have h of tau, you also need to find h of minus tau, which is the time inverted version of h of tau, right? And then you have to give it some shift. So here I would write h of, this is your h of minus tau, which you get from h of t, right? And you have a shift. We give a shift of t. So we give a shift of t to this one, and when we get this integral, when we get this product, we have to integrate it from 0 to t, and we would get the function y of t here. We will get the function y of t. And if you see, the output of this integral depends on this t. The output of this integral actually depends on this t, which is used as an upper limit, or which is used as a shift of these signals. So you have actually x of tau, h of tau, right? Then time inversion, h of minus tau, and then find this product, the shifted version and x of tau. You just find this product and then integrate it from 0 to t. And that would give you, if you shift it, why we call it the function of variable t. It's the function of variable t because this t, if you shift this t, if you change this t, the value of the output would change. So this integral, the value of this integral changes with this upper limit. A smaller value of t would give you smaller value, the larger value of t usually gives you the larger value for causal signals. So this is what you learn in the signal ramp system, and to be very specific, to be for the purpose of recalling that integral, if your x of t, if your x of, suppose your x of t is a pulse, right? This one, just a pulse. If your x of t is just a pulse, and you want to integrate it with another pulse, if you want to integrate it with another pulse which is same as x of t, so this is just the inverted version of your, suppose this is x of t, right? So this is the time inverted version of your x of t, which is x of minus t. You can say x of minus t. Let me call this one as h of t. Let me call it this inverted version as h of minus t. So you can always replace this t variable. So I'll just replace if I change this variable t and change it to tau, right? So let me change this variable. Changing the variable does not have any effect on the waveform, right? So this is h of minus. Now what if I give it a shift of t? If I give it a shift of t, now it means I am dragging this waveform here. If I put a shift of t here, if I put a t here, I am dragging it. So if you give it a shift of t seconds, you can say, so you are actually dragging it. So when t is 0, when t is 0, you just have the inverted version, which is shown here. When t is 0, you just have the inverted version. When t has some value, positive or negative, you actually shift it from, we usually in the integral you can see from minus infinity to plus infinity. The limit of t is from minus infinity to plus infinity. But as our signal is from 0 to capital T, right? Our signal is from 0 to capital T, so we would be interested in this duration only. We will be interested only where our signal, where the product of our signal is present. So when you give it a shift t, you actually what you actually are doing, you are just shifting it here. Suppose this is our next positive value, next value of t. So this is the value of t here. Now you will have a product because in the next step you have to multiply x of tau and h of t minus tau. So when you see this product would give you a value which is just this way, like the value this area multiplied by this area, because the rest here it is 0. This function is 0 here, so 0 multiplied by any value would give you a 0. So you just need to find out this product, and it would give you some value. You have to integrate it, right? You have to integrate it from, that is why we say from 0 to t, because in the remaining time and on the remaining axis, time axis, you do not have any, you do not have the value of this product. So we just integrate it from 0 to t, and we say our integral is giving us this value. Now once you integrate it for these specific waveforms, if you find this integral, you would get integral something like this. This is the output, right? Output. This is a t, this is a 2t, and we would see that once we drag it for different values of t, this is for t0, right? This output is for t0. Similarly, you can take the t equal to t over capital T over 2, and you would get this output from here. When you have t0, you get this value, right? When t is equal to 0, you get this point. When t is equal to capital T by 2, you will get this point. When t is equal to capital T right? When your time is capital T, you would get this point. Similarly, when your time interval, this shift is 3t, you can say here this value, which is 6t over 4, I guess. 6t over 4 or 3t over 2. 3t over 2. When your value is 3t over 2, so you would get this value. When your time, this time axis is 2t, you would get this value. So you just have to plot it. And when you plot the output of this integral is y of t would look like this. And we are sampling the signal at this instant. If you see in our diagram, we are sampling it in this instant where we get the maximum output, right? Where we get the maximum output, and this maximum output when your time is actually, when your t is actually time is actually equal to the period of this signal, and when we have this time equal to the period of the signal, our shifted version of this signal occupy. There is a complete overlap, or we can say that our shifted version is now, it moved up to here, it moved here. So you have a complete overlap, and complete overlap you have the maximum output, which is shown in this diagram. So this is how the matched filter, this is how the convolution actually works. So as I said earlier, that we have two orthogonal signals which has to be transmitted, and we would see the output of a matched filter. We would see the output of the matched filter at the receiver side. So let's try to find out the filter response first. So if you have S naught of t, which is a pulse, your filter response for S naught of t, the filter response for S naught of t would be H naught of t, and that H naught of t is actually equal to the shifted version, and the time inverted and shifted version of S naught. So this would be your response for the filter, the matched filter response for S naught of t. And if you specifically plot it, you can see that your S naught of t is this waveform 0. This is your S naught of t, right? So if you have a time inverted version, the time inverted version of this would look like, let me draw it. Time inverted version would look like this, right? The time which is S naught of minus t. Now this is actually S naught of minus t, right? This is the time inverted version. Now if you want to give it a shift of capital T, this would make this signal H naught of this response causal, because something before reference is unrealizable. So we want to make it realizable. The response should be realizable. So we give it a shift of capital T. When you give it a shift of capital T, you actually move this here. So the response, you actually move it here. Now this response, this is H naught of t, which is actually S naught of t, which is actually equal to S naught of minus t shifted by capital T. So this is the this is your signal, right? This is your response of the matched filter response, or you can say the matched filter matched filter response for S naught of t. We want the actually the impulse response of the matched filter should look like this thing. The impulse response of the matched. So this is how you find the impulse response of the matched filter for your waveform S naught of t, right? Now keep this in mind, this response, and let's try to find out the response of the matched filter when you have S1 of t. So when you have S1 of t as a signal, if you see S1 of t, which is a waveform, given by this one, right? Orthogonal to is from 0 to t. This is S1 of t. Now, if you invert it, the first step is to invert this one, because we should have H1 of t, the matched filter response. It should be the inverted version and the time shifted version. The inverted and time shifted. So when you invert it, it would look like this. Right? It would look like this, a time inversion. Now, if you shift it by capital T, you are actually moving this response. You are actually moving it to the right, towards the right, and this is the response H1 of t. Now, your H1 of t. Your H1 of t looks like this, right? So you have now H naught of t and H1 of t. This is up to capital T. This is 0. This is minus 2. So your response, you find out when the signal waveforms are given, you can find out the response, the impulse response of the matched filter that would give you the output which would have the maximum signal to noise ratio at the output of the filter. So at the output of the filter, if the impulse response matches this signal, the output is maximum. The output is at maximum SNR. So we just found the two impulse responses of the matched filter. And those two impulse responses, let me redraw those two. We have H naught of t, which looks like this. This is A. This is our H naught of t, right? Okay, this is H naught of t, and we have H1 of t, which looks like this. This is H1 of t. Now with these impulse responses, we expect that our signal, the signal waveform, the signal can be demodulated and detected in AWGN. It would be an optimum receiver with these impulse responses, because the signal would be detected correctly, ideally in the absence of noise, and it would have an optimum detection performance when the noise is there. When the noise is there, it would have an optimum detection process. We will see it. We will see the output of these filters shortly when we transmit these two signals. So let's suppose we transmit S naught of t. Suppose we transmit S naught of t. Now here we assume, suppose we transmit S naught of t. So let's see, when S naught of t is transmitted, what would be the response of the two matched filter, because we always our receives. First of all, we have to write the expression for our received signal. So when we transmit S naught of t, what we would receive is in the noisy channel is just AWGN noise. We would receive this signal, is what we received, right? Now the detector has to detect the received signal. It has to detect, it has to declare, actually it has to declare that S naught of t is received. When it declares S naught of t is received, only then we can regenerate a binary 1 successfully, right? So from this R of t, the receiver, match filter receiver, has to declare that actually S naught is transmitted. And let's see the outputs. Let's see the output of each match filter when S naught is transmitted. So when S naught is transmitted, we can write the output of the matched filter. We can write the output of the matched filter as S of tau H of t minus tau d tau, and we integrate it from 0 to t as I discussed earlier, right? So this is the output of the matched filter. So you can write it for the upper branch as well as the lower branch. Now when we transmit S naught of t, actually here we would have the received signal R of t. And if you see here, here we would have the let's discuss it in the absence of noise, and let's see the performance in the absence of noise. Let's assume that our R of t, which in the white Gaussian noise is this one, assuming that this part is 0, so we are left with only this part, right, R of t. So now you can see that when there is no noise, your output can be expressed in this form. Later on we will see the effect of noise as well, but let's see the ideal situation, and let's see the output of the matched filter when there is no noise. Of course, when there is noise, the output would be a noisy output, but it would look similar to this one. The concept is similar. So this would be our output. Now if we have S naught of t, here we would have S naught of tau and H naught of t minus tau for the upper branch. Now this is for the upper branch. This expression is for the upper branch of the matched filter receiver, the optimum receiver which we just discussed about. So in the upper branch, if I draw my upper branch only, you can see that the received signal passes through H naught of t, so there will be convolution, and you will have a y, and let me call it y naught of t. You will have this output which we will sample. We will take the sample of this output at t equal to capital T, right, and we will call it the first output from this branch. Now when this is the case, you can write your expression y of t here. Let's see this y of t. Now it should be this expression, as I said, that this expression is true for the upper branch for this one. So let's sample this output. When we sample this output at this particular instant, what actually we get, we are assuming now here we are assuming that our time instant t equal to time instant t. Now first of all I have to write it in this form, which is just okay. So let me take a fresh, let me move to the fresh slide, right? Let me move to the fresh slide. Now you have the signal y of t, which is or let y naught of t, which is actually s naught of tau and h naught of t minus tau d tau, right? This is what we have. With this integral, if we have h of now what do we have? We have h naught of tau, which is given by s naught of we just saw above. It is h naught of t is given by this expression, right? We just derived above. S naught of t is given by this expression. So what would be h naught of tau? It would be s naught of t minus tau, right? And now when you when you invert it, because we have to invert h naught of minus tau. Now see, h naught of minus tau, it would be s naught of capital T plus tau, right? And now when you shift it, shift it by instant t, h naught of t minus tau. So this would be, now we are substituting t minus tau for this tau. So this would be s naught of now instead of tau, okay, see it over here, instead of tau you have t minus tau. So instead of tau you have t minus tau, and this would be when you substitute it here, yes, here, this expression, so you would get capital T minus t plus tau, right? You would get this thing. So this is your response, s naught of capital T minus t plus tau. Now you can, what you can do, I hope this is clear now, because we just shifted this one. To be very specific, we made it from this one. First of all, let me explain it again. You have h naught of t, which is given by this equation we derived earlier. We just said that this is the this should be the match filter response from the if we want to get the maximum the output at maximum SNR. So this should be the match filter response. Now h of, because for the convolution we always change the variable, so change the variable t to tau, we just change this variable. Now we are replacing it, this variable by t minus tau. So when you replace this variable by t minus tau, you have to replace this here, right? So when you replace t minus tau there, you get this thing. We just replace this one. So this is your response, h naught of t minus tau, right? Now we substitute, we would like to substitute this response here, h of t minus tau. So when you substitute this response here, what actually you get, your equation becomes something like this. You see, your equation is now y of t, which is the integral from 0 to t, s naught of tau, and you have h naught of t minus tau, which is equal to s of t minus t plus tau data, right? This is actually s naught. This should be s naught because we have s naught here. So this is the output of the upper branch. This is the output from the upper branch. Now if we want to sample this signal, if you want to sample, because this is just the expression for the output, we want to sample this signal at t equal to capital T. So just substitute t equal to capital T. So you would get y of capital T, and this would be from 0 to capital T, s naught of tau, right, and s of capital T. Now we have to replace this t by capital T, right? So we have to replace this t by capital T, and we have the expression, right? So we just replace this t by capital T. Now if you can clearly see that this cancel out, and you have s naught of tau and s naught of tau. So you have the square of the signal. So you have actually you are integrating 0 to t s naught square beta. So your y of tau, your y of capital T, which is the sampled version, is actually equal to the square of the signal, and the integral of the square of the signal from 0 to tb, right? Let me rewrite it here. 0 to t, this is 0 to capital T, and you are integrating the square of this signal. So when you integrate the square of the signal, this is actually equal to the energy of the signal. So this is actually equal to the energy of the signal. So this is actually E, energy of the signal, E sub s. So your y of t is actually equal to the energy of the signal, right? So this is the energy of the signal. Now we see that the time instant is important. This time instant where we sample this signal at the output of the match filter, this is important instant. We get the energy of the signal here, right? Now this energy of the signal is in the upper branch. Now the same signal passes through the lower branch. If you observe, the same signal passes through the lower branch. Well, before going to the lower branch, let me discuss it graphically now. Let me discuss it graphically. Let's do that analysis first, and then we'll discuss it graphically, right? Let's do the analysis first. So let me move to the fresh slide. Now what I would like to do is the same signal also passes through the lower branch, and the lower branch R of t, it has a matched filter which has the response h1 of t, right? So h1 of t is actually equal to s1 of capital T. This is the impulse response for the second branch. Impulse response for the second branch, which matches to the second signal S1, the orthogonal signal S1. Now when we can write, because our R of t is S naught of t, which is transmitted, so our Y1 of t, we can write Y1 of t as a convolution of S naught of t. Let me write, this is the convolution of S naught of t and H1 of t, right? And you can write this convolution, convolution integral as S naught of tau and H1 of t minus tau d tau, and from 0 to t. So this is your y1 of t. This is the output y1 of t. Now we can solve this in the similar way. you can say that your H, if you observe here, now you will see that these two actually H1 H1 T minus tau. If you observe this product, it at that particular instant when T is equal to capital T, this product gives you this is because these S naught of T and this product are orthogonal. We will see it just in a moment. We'll see it in a moment. These are orthogonal, so you will get 0 at T equal to capital T. So first of all, we have to write the equation for y1 of t. So we just said that okay, our y1 of t is given by this equation, and here we can say that okay, this is 0 to t s naught of tau and h1 of t minus tau. Now here h1 of t minus tau is actually equal to s1 of t minus t plus tau, right? Similarly, as we did it for in the above slides, we did it for s naught of t. So you can verify that h1 of t minus tau is actually equal to this s1 of capital T minus a small t plus tau. Now, if we sample this once again, we have to sample it at t equal to capital T. We have to sample it here. Now, once we sample it at this instant, it means we are replacing here this t by capital T. So, if we replace it by capital T, we would get the signal at capital T, right? And this t is equal to capital T. Now we are taking this sample. We want to find out the value of this sample. So if you observe this sample value, actually you can rewrite this expression now, and your expression from 0 to capital T is s naught of tau and s1 of tau, right? S1 of tau deta. Now we have seen that these two signals are orthogonal. These are actually orthogonal. So you will get this output would be 0 at t equal to t. This output would be 0. So this is how we said that okay, from our match filter, where we move this received signal through two branches. We forward it through two branches with the two match filters, and we sample it, right? We sample these output. This is y0 of t and this is y1 of t. And when we sample these, we get two outputs at t equal, this sample is at t equal to capital T. So we get this output which we call R0, and this output as R1. So R0, we just saw that R0 is actually equal to the energy of the signal, while R1 is actually equal to 0, right? R1 is actually equal to 0. So when these two values R0 and R1 are given to the detector can easily verify that this just a threshold detector which just try to find out which one is greater. So this, of course, this output, this energy is greater than 0, and the detector would declare that S0, the upper branches for S0, so it would declare that S0 is transmitted, and it can regenerate a binary 1. It can just output a binary 1, make a decision that a binary 1 is received. So this is what we were expecting from our match filter receiver, that the output, it should declare that the output is 1 when we transmit S0. When we transmit S0, you can repeat this process. You can repeat this process by just assuming that just suppose you can just repeat this process by assuming that S1 is transmitted. If S1 is transmitted, now if S1 is transmitted, your received signal would be S1 of t plus noise, right? Just try to solve it in the absence of noise. Try to solve it in the absence of noise, and then once we solve it in the absence of noise, we can always add noise and see the analysis. Now if you see what will happen if you see the noisy signal, right? Now in this case you when you receive when you transmit S1, you would and you analyze it, you would see that R0 is actually 0 and R1 is actually equal to the energy of the signal S1. So you would conclude this. When you conclude this one, it's easier for the detector. The next step is to make a decision whether it is S0 or S1. So the next step is easier, and the detector can easily decide whether S0 is transmitted or S1 is transmitted. So this because it has two values, 0 and some positive value, a 0 and some positive value, these two. On the basis of these two values, the detector can easily decide whether S1 is transmitted or S0 is transmitted. So this is how the match filter works. The match filter receiver works, and it gives you the output which is at maximum SNR. Keep this in mind. Now let me show you graphically. The signal waveforms. The signal waveforms which would be at the output of these two matched filter. Now if you see the responses, of your filter, I'll draw it here for this is the response, the impulse response of the matched filter, which is actually equal to S0 of capital T minus. Right, this is the impulse response of the matched filter for the upper branch. Similarly, you have the impulse response H1 of T, which we just saw above, that it is actually a pulse which is like this, from 0 to capital T, minus A plus A. Right. So this is the, and this is actually this H1 of T is actually equal to S1 of T minus small. This is time axis. So we saw these responses. When we initially we assume that we are the transmitted pulse is S0 of T. So initially we assume that the transmitted pulse is S0 of T. Right. Now when you convolve the upper branch gives you the convolution of H0 of T and S0 of T. When you convolve these two, the output would look like this. We just saw this output in detail in the beginning of our lecture. So the output would be like this, and here you can see that the output is maximum at this point, and this maximum is actually equal to the energy of the signal, which we denote by ES0. The energy of the signal. This output is actually equal to the energy of the signal. Now when you convolve these two, because in the lower branch the convolution of S0 with H1 is there. When you convolve these two step by step, just do this convolution step by step as you have done it in your VS course. Just and that is to first of all you have to find H1 of tau, right? H1 of tau, which is just replacing this variable, and then H1 of minus tau, inverting it, so you would get a signal which would be like this. minus tau, h1 of minus tau, and then you have to drag it here. You have to drag it here. When you drag it here at towards the right at t equal to capital T, you would see that this waveform would look like this. It would look like this. Now at t equal to capital T, this waveform is like this. So it's just orthogonal in that case. So when you drag it step by step and you try to find out the product of these two waveforms, drag it and try to find out the product of these waveforms, and you can do it in the MATLAB as well, or the Octave. You can use Octave for simulation purpose. You get a signal which is just like this. You get this point at capital T. Similarly, it would be like this. 2t onward, no points, right? From 2t, this is up to 2t, and from onward there is no point. And you would see that this value, you can always compute this value. This is actually at when t is equal to t over 2. Let's substitute t equal to t over 2, and you can compute this value, which would be minus a square t over 2. You can always compute this. Similarly, this value would be plus a square t over 2. We just solve that integral for t equal to t over 2, and you would get these values, right? You would get these values. So just try to find out these. This is the output from the upper branch, the output at the lower branch, at the output of this is the output at of the mesh filter at the lower branch. So when you sample it at t equal to capital T, it means you are observing this value. You are observing this value, and here it is here, these two values. You are observing these values. Now here, when S0 is transmitted, you have the energy of the signal, and while in the second branch you have 0. This is what we proved mathematically, and here you can see it, you can just verify using Octave, and graphically you can prove this, that you get these signals here. So this is how the when you sample these values, just give it to the detector and it can decide in favor of just threshold detector. It would see that this threshold, this value is greater than this value, so it would decide in favor of S0. The detector, the maximum likelihood detector, would take decision in favor of S0. So this is how the matched filter, the output of the matched filter can be obtained. You can do it mathematically. Just try different signals, do it mathematically, and do it analytically as well, mathematically as well as graphically, right? So you have to do it in both ways. Now, as we said that we discussed the ideal situation, assuming that our received signal, in the first case we said that our received signal is this one, but we just ignored this part. Now if we include this part, which is the noise, if we include this part, we can conclude we can conclude that our R0, instead of only the energy, it would have a term N0, which is the noise term. It is actually an integral, definite integral, so it gives you some value. Similarly, R1 would, instead of 0, it would be a noise term, an integral, and this is additive white Gaussian noise term. So these terms which appears due to noise gives you the noisy term. Now what will happen graphically if I show you the effect of this noise? Ideally you get this waveform, right, from the upper branch, and you get this waveform ideally in the lower branch. When you have noise, you would see that this you may get some distorted waveform or something. not exactly this black line. It may be something like this. Similarly, in the lower branch there will be effect of noise, and you may get some distorted waveform, which is the effect of noise. This one, it may be something like this, right? So when you sample at this instant, t equal to capital T, you still get this value, but now this value contains the value of a signal energy, which is this term, and it also has the noise term, which is N naught. Similarly, here you may have the energy, you may have 0, and the noise term may be non-zero. It may be non-zero, right? It's non-zero value. So it may have some value. So still, most probably your detector, maximum likelihood detector, in a noisy case would decide in favor of S naught when you transmit S naught, because this sum is expected to be greater than this value. This sum is expected to be greater. R naught is expected to be greater than R1, most probably, even in the presence of these noise. But it may also happen that sometimes, which is rare, that sometimes N1 this value N1 is greater than this sum. So then the detector would take a wrong decision. But most probably it would find that R0 is greater than R1. When you transmit S naught of T, it would find that R0 is greater than R1. So it can decide in favor of S naught. Your receiver can decide in favor of S naught, right? The same decision we can just repeat it for the when you assume that the transmitter has transmitted S1 of T, then of course the receiver R0, instead of receiving 0, it would have this output, and it would have this output in case of noisy signal. And this N naught is nothing but the integral. This is, if you see the N naught, this is nothing but the integral of the noise with H of T, right? Or it is nothing but the let me specifically, because you convolve the signal with the noise, so this N naught would be the N of T convolved with H of T. And see, this is because now you can find out this integral. You can always find out this integral. If you try to find out this integral, you would conclude that your N naught is actually equal to 0 to capital T. At instant T equal to capital T, this would be equal to the noise signal N of tau, and H of the H in term, I would write H in terms of this would be equal to S naught of tau. This integral would be equal to this value. We can find this, you can just solve it the same way as we solved it earlier. And similarly, N1 when S naught is transmitted, you can find it out that this is actually equal to N of tau and S1 of tau, right, beta. You can verify this. Just substitute the value of H of T in terms of S naught of T, and just take this, replace T by capital T there. And you can find it out there, just there in that convolution, that your signal is actually these two. So this is how we mathematically see the outputs of our matched filter, and the sampled outputs of our matched filter. The sampled outputs at the sampled values at the output of the matched filter. So these is how the matched filter receiver works. So I suggest that you go through these analysis, specifically which I left for you people, go through those analysis and verify that your signal R of t, you just verify that your signal R naught is actually equal to R naught is actually equal to the energy of the signal plus noise M naught term when you transmit S naught, and it is 0 plus N1 term when you transmit S naught of t, right? And also verify that your signal is R naught is equal to 0 plus N naught, and R1 is equal to energy of S1 plus N1 when you transmit S1 of t. Now you need to verify these. The presence of noise, you can always use octave for the purpose of verification. Do it mathematically as well as in octave.